welcome to Steve Nichols, and thank you very much for joining us and giving us this presentation. I'm sure everyone will find it very good, very entertaining, very knowledgeable. Yeah. So, I don't know. Do you want to give us a brief introduction about yourself? And
yeah, sure. Well, my name's Steve Nichols, G0KYA. I'm the chairman of the RSGB Propagation. Doesn't necessarily make me an expert; it just makes me a kind of a how do I explain it? Lion tamer, I think, to keep all the various members of the Propagation Studies Committees. There's about 8 full-time members of PSC and about another 20 members who are associates, so we can call on them when we need help, as it were. But understanding HF propagation has been put together for quite a while, but I've updated it today to include some latest information. And what we're going to do, we're going to talk about what the main factors are behind propagation, what makes good propagation, bad propagation, and finally at the end we're going to look at propagation prediction programs. And we're going to start by looking at what we've done with RadCom, and then look at what we've done to enhance RadCom with RadCom HF predictions online. Okay, well, you should be about an hour, I should think, if that's okay. Some funny noises coming on there. So do you want me to get going then?
Yeah, it's Hawkins, I think. Hawkins, if...
Sorry, mate, I rejoined the stream and was still on, had audio back on.
Okay, so you can all see the Understanding HF Propagation slide, I guess.
Yep.
If so, okay. If so, I'll start. Okay, well, let's get going then. So really, HF propagation all comes down to the sun, or 99% of it. And the sun emits massive amounts of electromagnetic radiation, that's ultraviolet and X-rays. And put simplistically, the more sunspots there are on the sun, the more ionization we get. That is an oversimplification, but it will do for now. And one thing we start off with here was we measure the solar at 2.8 gigahertz or 10.7 centimeters of wavelength, and that gives us a solar flux index figure. Now, let's just get this straight from the start. It's not that radio frequency emissions that causes the ionization. A close tally between that ionization and the 2.8 or the 10.7 figure. So it's a good proxy for how much radiation is coming off the sun. And we've been using this figure for quite a long time now, many, many years. So the SFI, or solar flux index, is one of the figures we use to measure the output from the sun. And if we have a look at, this is a chart of the solar flux progression cycle, and as you can see, we had the peak there 2024, and this was updated today where we are sort of on the declining side of cycle 25. It says 24 there, it should say 25. I didn't update it. Solar flux index, it can be as low as 65 or as high as 274, and it can even get up to about 300. Today it was about 120, I think, which is still good enough to get 10 meters open, and that's probably the one figure that we can remember, that if the solar flux index is above 100 and we're in the right time of year, 10 meters can open up. So at the moment, 120 or thereabouts is good enough to get 10 meters open, and that's a good sign. Now, obviously, there is another way of doing it, which is to look at the sunspot number. And this is the graph of the solar cycle 25 by looking at the smooth sunspot number. We call it a smooth sunspot number because we take an average or moving average over the last 6 months. So you can see there that again, it peaked at the same point, and we're on the decline again. And you can see we're slightly below where the prediction is of where we should be going. And you can see from that red line there on the right hand side of the table that that's where we think things are going to go. So at the moment, things are going to go quite well, but they're going to tail off over the next couple of years until we get down to sort of 0 sunspots or thereabouts, or a solar flux index of kind of 68, 70 or thereabouts, to see where we are. So that's where we are on the cycle anyway. So we've had the peak, we've had the fun, if you like, and we're on the declining side. But it's not all bad news, as we'll show you later. Now, what does the difference? What difference does it make? Well, this is a G6EL prop, I think it was, that shows you the propagation between the UK and New York in October for solar flux index levels of 65 and 275. And from that, you can see that at 275, it's up there, sort of 30 megahertz plus, I think. And so that's why we get good 10 meter openings in October to America. But at sunspot minimum, when it's at 65, you'll see it'll really, really struggle to get up to, I think, 20 megahertz, I think, or thereabouts. So that's the difference between the two. So obviously, sunspot maximum is a good time for worldwide DX, but it's not the be all and end all. We can still work it outside of sunspot maximum. Now, sunspots really help with propagation, but there are things coming from the sun that don't help with propagation at all, really. And the first one I want to look at is solar flares. And high sunspot activity can also bring solar flares. And as I said there, it can be quite devastating for the HF bands. Solar flare is something that emits massive ultraviolet or X-ray output radiation, and it causes massive delayer absorption and therefore poor conditions. The good news is that solar flares the effects don't last that long, maybe 1 hour, maybe 2 hours, but you can get, 8 minutes after this flare appears. Well, actually, that's not quite true. I was going to say 8.5, 9 minutes after the spot appears, but of course, it's at the speed of light, we're seeing it sort of 9 minutes after it happened anyway. So by that time, the electromagnetic radiation has already hit the Earth. So you can get what you can call a sudden ionospheric disturbance, or an SID, and that can close the bands down. So if you're listening on HF and suddenly everything goes quiet, it may have been a solar flare. And we have had quite a few of these recently. We had some X-class solar flares, and we'll talk about what classes are and the effects shortly. But so that's the first thing I want to talk about, is solar flares, which are not really conducive to good HF propagation. So as I said, solar flares are classed according to their severity. So you'll see them classed as A, B, C, M, and X class solar flares. Most of the systems online tend to talk about just the C, M, and X class solar flares, and the C class is the lowest severity, and X class is the worst severity. So X class flares are the one that cause the most damage. We have had some X class flares recently. I just want to go back from that. Okay, so as I said, each X-ray class category is divided into a logarithmic scale. So you get B1 to B9, C1 to C9, M1 to M9, and X2 flare is twice as powerful as an X1 flare, and 4 times more powerful than an M5 flare. So you can see that it's a little bit complex to work out how strong a flare has been. But really, the ones that cause us the biggest problems are M-class and X-class flares. C-class, not so much. So if we have any M-class flares, that'll probably affect the ionosphere, and an X-class flare definitely will. So this is the effect of a solar flare. So you can see that the signal strength can instantly go down and then recover over the period of an hour, perhaps. But you'll also see that solar flares affect the lower bands more than they affect the upper bands. In fact, at 28 megs, you may not even see the effects much at all, but maybe down at, well, say 5 megs here, or 3.5, 5, 7 megs at that thereabouts, solar flares have a disastrous effect on propagation. And that's because this ultraviolet or X-ray radiation penetrates deep into the D layer of the ionosphere. And that's the one that's responsible, at HF anyway, for absorption. So an X-class solar flare can cause this massive sudden ionospheric disturbance, and recovery time can be 1 hour or thereabouts, maybe less, maybe more, depends on how bad it is really. But maybe at 20 megs or 28 megs even, you may not even see the effects of a solar flare, or they'll be quite minor. So that's the first thing we need to look at in terms of what affects propagation. So if you think of a chart, you can think sunspots are on the left-hand side, they're good. On the right-hand side, the bad. Solar flares is the first one. But there's something which is even worse than solar flares, and these are something called coronal mass ejections. Now, these are often linked to solar flares, and this is when basically the sun burps, if you like. The sun emits a big cloud of plasma, which can be ejected into space. And you can see how big that CME is there, because you can see a little tiny image of the Earth there. So you can see that CME, an average CME, is massive compared to the size of the Earth. It is absolutely enormous. And these are high energy, high output clouds of plasma. Now, it depends on whether the CME is pointing directly at Earth, or whether we get a glancing blow, or it might miss us completely. So it really depends where the solar flare and the coronal mass ejection appears. So for instance, if you get a CME coming off the center of the sun, directly facing the Earth, that's about as bad as it gets. It's really going to affect us. And if you look into the speeds of these things, I mean, sometimes 600 or more kilometers per second, which I calculate to be 1.35 million miles per hour. So they are fast. I wouldn't want to be an astronaut out in space, maybe doing a spacewalk, and a CME comes past. I mean, you'll be hit with, you know, a billion tons of plasma traveling, you know, 1.35 million miles per hour. So it's not terribly good for your health. Well, not good for radio either, but there we go. So that's what a CME is. So they're associated with solar flares. You can have solar flares without CMEs, but generally, do you have CMEs without solar flares? Yes, you can, but generally they are linked. If you have a solar flare, you may have a CME at the same time. So these CMEs, as I said, can head towards the Earth, big cloud of plasma, and where these particles get channeled towards the poles. Now, the other thing we can say about a CME when it is erupted from the sun is that it has a built-in frozen magnetic field as it leaves the sun, and that magnetic field has a direction. So we call that the BZ, and if that BZ is pointing south, so we've got a south-facing magnetic field on this CME, that's not very good news for Earth, because just like with bar magnets, if a south-facing interplanetary magnetic field hits the Earth, it's more likely to couple with the Earth's magnetic field and more likely to come in. But other than that, you can see that that CME plasma is hitting the Earth, and it's bending the Earth's magnetic field backwards, pushing it, push, and causing these field lines to stretch out behind the Earth like that. And when these magnetic field lines reconnect at the far right-hand side of that picture, then it can instantly cause the CME material to flow back towards the Earth, and that's when it hits the poles. And guess what we get when it hits the poles? We get an aurora. So if we get a aurora, polar aurora, northern lights, we get an equivalent southern aurora australis, or southern lights as well. So there we go. And you can see the effects of this on solarcycle24.com, which is a free site for you to use, which has lots and lots of stuff. But one you can click on is the ACE HF satellite or spacecraft graphs, and it will show you the speed of the CME. It will show you the BZ, whether it's pointing north or south, and its density, temperature. But as I said, if the BZ points south, that is more likely to cause problems on Earth. It's generally bad for HF as well. If we do get these fast CMEs hitting the Earth with a south BZ, you're more likely to get aurora, which we have had in the last few days actually. And it has a pretty disastrous effect on HF as well. So we measure the field strength of these things in nanoteslas. We used to, in GB2RS, we used to use, or tell you what the magnetic strength of the CME was in nanoteslas, but I kind of, when I took it over, I banned the term because telling somebody that, you know, you've got a 10 nanotesla magnetic field doesn't really help you. It doesn't tell you whether it's good or bad. But just to give you an idea, though, we have an average of 10 nanotesla for the magnetic field of a CME. The Earth's magnetic field is about 50,000 nanotesla, so that's 5,000 times stronger than the CME magnetic field. And to give you some idea, an MRI machine is about 1,000 million nanoteslas. So it's quite a weak magnetic field, but it's enough to affect the Earth as well. And it affects magnetometers on the Earth as well when it hits. So what are the effects then on HF? Well, initially, as the CME hits the Earth, the conditions can improve very slightly. And you do get this. It's called a pre-auroral enhancement. And you do see MUS just rising very, very slightly, maybe for half an hour or so. But as the aurora progresses, we generally find that the maximum usable frequencies and critical frequencies reduce as the F layer is depleted. And what you can find is that paths, HF paths that pass through the polar regions, that's south and north, they can be worst hit. So such as a path from maybe the UK to Western Canada. So the area sort of where Victoria and Seattle, what's the other place I'm thinking of? Vancouver, that's the one. You know, you may find it very difficult to work those sort of areas. But on north-south paths like the UK to South Africa, you may find it has no effect whatsoever. And generally, recovery from a CME can take days, can take 2 or 3 days for the ionosphere to kind of rebuild itself and stabilize. But at the same time, if this is happening, then you get auroral conditions on VHF. And we do another presentation when we look at auroral effects. So CW, for instance, just sounds like hissing kettle, sort of very odd. It's worth listening to some VHF signals when there's an aurora on, because they are bizarre. You know, they're constant Doppler shift off this aurora, and they do sound very odd. But I think hissing kettle was the best description I've ever heard. This photograph, by the way, I took this in Iceland in 2014, and that was with a KP index of 3. We'll talk about KP index in a minute, but that was aurora over Iceland with a not particularly high KP index, but it was visible aurora. To the naked eye, it looked a bit fuzzy. It didn't look like that, but with a camera taking a sort of time exposure, I was able to get that picture from Iceland. There's a long story behind that. I went with my daughter who was studying for her GCSEs, and yeah, that was February, so it was no, it was April actually. April, yeah, that's right. So it's never warm in Iceland that time of year, but it was freezing cold with a high wind, and we were outside at midnight taking photographs of aurora, but happy with it, you know. So the K index is a method we use to show the 3-hourly effect of these particles interacting with the Earth's magnetic field, and because it's 3-hourly, it's the most up-to-date measure, really, of this disruption. Now, you might have heard of the A index as well, and the A index is a more it's an average of the index over the last 24 hours. So it's very possible to have a high K index, but have a relatively low A index, because the A index, being an average of the 24 hours, doesn't tell you what the up-to-date situation is. So generally, on GB2RS, we use the K index because, or KP index, the planetary K index, because it's more up to date. It's never more than maybe 3 hours out of date. So you can actually plot this. You can actually plot the speed of the solar wind using that chart I showed you at solarham.com. And if you see the speed go up and the BZ points south, then you know that the K index in 3 hours time will get bad. But the A index might not show for another 24 hours. But just a thought. That's why we generally just use the K index rather than the A index, because a K index of 5 or more generally hints that we've got aurora coming. And if we get, I think we had a KP of 7 the other day, that basically is, yep, you're going to see the aurora in the UK. That's the thing to look at. I had to laugh the other day. There was a story saying, oh, you know, aurora are going to be showing tonight. And I thought, well, no, they're not, because the K index had recovered to about 3 by then. So there was no way you were going to get an aurora with, in the UK with a K index of 3. But there we go. That's the media for you. So as I said, if you've got a path that passes through the poles, like this one here, which is Western Canada from the UK, you will have problems if you've got a high K index. A K index of maybe 4 or maybe 3 or 4 or higher is going to cause you problems on that G to VE7 path. So the best thing to do on polar paths is look for when you've got low K indices. And by low, I mean 0, 1, or 2. That probably won't cause you much of a problem. But if you are trying to work that kind of part of the world, and it's a polar path, then if the K index is high, you're probably not going to do it at all. So there we go. Okay, so let's talk about these regions now. We often hear the D region, E region, F region mentioned. This gives you an indication of how high they are. So the F region is the used to propagate signals in the HF spectrum, notably 1.8 to 30 megahertz range. F region basically splits into 2 when the sun is out or in daylight. You get the F1 region, the F2 region. They combine just after sunset into a single F region until the following day. The E region, slightly lower there, is propagation on the lower HF bands, notably 1.8 to 7 megahertz. E region propagation generally is kind of a shorter distance than F region because it's lower, so you don't get as far. And finally, at the bottom there, we've got the D region, which is for what we're talking about tonight is an absorption layer. This is a region 75 to 95 kilometers up. And it's an area of absorption at HF. Now, the reason I say absorption at HF is because the D region actually does reflect signals, but only at VLF. So if you read about VLF, you'll find that the D region actually can reflect signals at VLF. But for our purposes, for HF, we think of it as an absorbing region. So when the D region gets excited by solar flare, for instance, that's why lower signals, 1.8 to 7 megahertz, don't get through too well. So one of the other terms that we use is the critical frequency. We often talk about critical frequency. Well, what is that? Well, the critical frequency, or FOF2, as we call it, F0, F2, is the frequency at which a signal that's sent straight up from the ground either returns or it doesn't. So in this instance here, we've got a critical frequency of 5 megahertz, and you can see the 5 megahertz signal going straight up, hits the F2 layer and comes back down again. But if you look at a critical frequency of 5 megahertz, if we send a 10 megahertz signal up, it's just going to go straight through into space. So that's what we mean by a critical frequency. And from knowing that critical frequency, we can then extrapolate, if you like, to work out what the maximum useful frequency is between 2 points on the Earth. So this is why the critical frequency is so important. This is also important if you want to do what's known as near vertical incidence skywave signals. So if you want to chat to your friend just down the road on 3.5 megahertz, say, or 7 megahertz, then the critical frequency has to be above 7 megahertz, obviously. And at sunspot minimum, the critical frequency is usually below 7 megahertz. So 7 megs is not a good band to use to talk around the UK, basically, at sunspot minimum. At the moment, it's okay because 7 megs will get you around the UK. Although what you sometimes find is you can talk to people in Scotland find on 7 megahertz, and you can talk to people in near Europe, say France, Germany, but you can't talk to people maybe 200 miles away in the UK. And this is why, because the critical frequency is too low. Basically, your signals are having to go up at such an angle that they are going straight out into space, or near vertical incidence skywave signals are going straight into space. So that's what we mean by critical frequency. Now, we can measure the critical frequency using something called a digisonde. And this is a plot of a digisonde here. And you can see that they're not the easiest things to read. They're a little bit complex, but we can use the chart on the left. This, I think, is from the Chiltern digisonde. And the critical frequency here is 4.625 megahertz, I think. So that tells me that if you were trying to work around the UK on 7 megahertz, no, you couldn't. You couldn't work 200 miles down the road, maybe 100 miles down the road, but you could work maybe someone in Scotland. On 3.5 megahertz, yes, you could, because your signals can go straight up and still come straight down again. So this is why digisondes are so useful to us, because they tell us what's going on. From that, we can extrapolate and work out the best frequency to use over various distances. You can see the digisonde plotted across the bottom there has got the frequency or maximum usable frequencies over different distances. So this is why critical frequency is very important to us. Okay, let's move on. And this is what's actually happening. So why do radio waves bounce back to Earth? Well, bounce is a bit of an odd term. We use the term bounce, but it's more of a kind of continuous internal reflection, if you like. So this shows you that our high angle rays there are being bent, but they're not coming back down. They're going out into space. That's the first one. The second one is being refracted, but it's going out to space again. And then the third and fourth ones there are being refracted off the layer and are coming back down due to total internal reflection. So again, this is another way of illustrating how sometimes you find that you can't work close in stations, but you can easily work into the southern Europe or far east of Europe, for example. And this is why, because your signals are, the low angle signals get through, but high angle signals just carry on into space. So again, this is all down to the critical frequency again. So we talked about this D layer. It's absorbing, attenuating signals on 160 to 20 meters, can reflect signals at VLF. But this is why we don't hear much skip, if you like, on the LF bands during daylight, especially in summer. For instance, top band and generally top band and 80 meters during the daylight, especially this time of the cycle, are pretty dead during the day because the D region has just got so much absorption. So it's a combination of the frequency, the time of year, the day of year, and the solar geomagnetic levels. So yes, if you've got a high solar flux index and it's, what should we say, March to September, then that D layer is going to be pretty well absorbing HF signals and won't be too good for you. This is the equation for the absorption, and I wouldn't worry too much about it. All you have to realize that is that the lower the frequency, the more the absorption. That's what it says. So frequency on 28 megahertz, the absorption is going to be an awful lot less than it is at 3.5 megahertz, which is why, preferably, if you're trying to work DX, you want to go as high in the band as you possibly can. So you find the highest band that is possibly open to you, and that will offer you the least absorption, and then you can actually try and work the people, which is why 10 meters is so good at sunspot maximum, because yes, you can work Australia like they're next door, but this is why you don't get as much absorption on the higher bands. But come down to bands like 3.5 megs during the day and try and work DX, you won't get on very well at all. But you have to wait for the sun to set, and then 3.5 megs, especially in winter, comes into its own. So the only thing you need to remember really is that statement at the bottom, that the lower the frequency, the more the absorption. So if we put this together, what do we get? Well, this is a chart showing you the lowest usable frequency on a path at sunrise. You can see that the frequency goes up, the lowest usable frequency goes up as the sun rises and then goes down at sunset. But now that's the lowest usable frequency. Now we can add the maximum usable frequency on there as well, and you can see that frequency, maximum usable frequency, goes up at sunrise and goes down at sunset. So basically you want to work somewhere in between those two, and we have something called the FOT, frequency of optimum transmission, or it's a French term actually, but frequency of optimum transmission explains it. So you can see there that you know, the best thing to do if you want to work DX is just follow that MUF, or frequency of optimum transmission during the day, and you can see that around about midday is usually the highest point, maybe slightly after midday, and then come sunset it goes down again. So this is why, say, 10 meters doesn't work terribly well after dark. It stays open for a little while, but it depends on a lot of factors. So finally then, let's look at some of the tools that are available online to you. Years ago we used to use PC programs such as W60L prop, VOA prop, VOA cap, and you had to run it on a PC or a Mac. You could run some of them on a Mac, but now everything has gone online. So VOA cap online is the online version of VOA cap, and it's free to use. You go to vocap.com and you can come up with charts like this. So this is a chart of your availability, or the likelihood of availability for a particular frequency, the optimum frequency to, or basically it tells you how likely are you likely to get to where these places are. So you can see there that the hotter the color, the more likely you are to get propagation. So basically this, with vocap online, you put in where you are, you put in your mode that you want to use, and you put in your power and your noise situation, and it will come up with a chart like this. So you can see from this that if you wanted to work northern parts of South America, if that makes sense, sort of Guyana, the rest of them, then you just about do it on this frequency here at this time of day on this, with this chart. So get to know how to use vocap online. It's a very, very good program. It's been done by a Finnish amateur, and he's done a damn good job. But again, you don't have to install anything on your PC or your Mac or your iPad or whatever you're using. You can go to vocap online, vocap.com, and plug all this information in, and it will show you the likelihood of working a particular location, a particular time of day. Or you can do this, which is a point-to-point chart, and this shows you the relative likelihood, relative circuit reliability for working New York from the UK at this particular time of the year. And you can see that this chart looks very similar to that one I showed you earlier. So you can see that the sun rises. Let's show this. So the sun is rising here, and the MUF rises at the same time. And the lowest usable frequency also rises. That's due to absorption. So as long as you're staying in this sort of period in the middle here somewhere, you should be able to work that station. So you can use these charts to work out the best times to work parts of the UK, or sorry, parts of the world. I'll tell you a little story now. I used these when I was trying to get my Worked All States award. And because I think you have to work 50 states, and I got about 48. And the two I wanted was South Dakota, I think, and one of the others, South Dakota and Wyoming, that's it. Well, there's not many hams in Wyoming and South Dakota as it is. So you've got to find the best time to work them. And it turned out there was about half an hour opening to work these places. And I actually did it on FT8. I wanted to do it on CW, but I couldn't. I had to do it on FT8. So I've got the Worked All States award now, but it was only by using charts like this that I could work out the best time between the UK and Wyoming or South Dakota to actually work these people. But that's why it's so good. This is another vocab online chart. So this is called a propagation wheel. And this, again, shows you the best time to work the UK to New York. And it's like a 24-hour clock. So you come around here and you look for the hottest spot. There we go. And then you look at the frequency as well. So you read the frequency off there and the hottest spot. And again, that shows you that you've got kind of a 60–70% chance of working them. So they're very useful tools. If you want to know, these are very useful for de-expeditions. For example, when we just had Bouvet Island, and it was a good idea to just chart the best time to work Bouvet Island using these tools. As it was, the trouble is that most of Europe wanted to work Bouvet Island as well. And although you could hear Bouvet Island, it was very, very hard to work. And I eventually decided that I wasn't going to get to do it without a linear amplifier. I could hear them every day, but could not get through for the life of me. But I've used these on other expeditions, and it works quite well. All right, well, what's the other tools that we can use? Well, one is to use the RSGB propagation chart, which is in the back of RadCom every month. It's produced by Gwyn, G0KYA, and it's produced using something called the ionosphere HF prop program. And basically, it shows you 24 locations around the world. Some of them, I think it's about 3 or 4 are long path and short path. New Zealand is worth, and Australia is worth noting the long path conditions as well. And it will generally show you the signal strength you can expect from that country. And this is based on 100 watts to a dipole. And we changed it recently so that it's color coded now, so it's easier to read. And also we changed it so that for FT8 and FT4, you now get a colon instead of a dot. A dot on there means that you probably can't work the country. But a colon says you may be able to work it with FT8 or FT4. We did actually use a system of letters as well, but talking to people at Hamfest and whatever, I found that it just confused the hell out of people and they couldn't understand it. So I had a word with Gwyn, and he said, yeah, okay, so, well, we had a big discussion as a group of us, and we decided to use a colon instead. So if you've got a colon on the chart at the month you want, then there's a good chance that you can work that station on FT8, FT4, which of course can work below the noise level. So there we go. So the RSGB tables are very, very useful, but they only show you 24 places to work, and they're based on 100 watts sideband to a dipole. So what happens when you have got a kilowatt to use into a beam? Well, you can work a darn sight more. Or what if you're a foundation licensee, so you're running 25 watts maybe to a dipole or a compromised antenna, should we say, multi-band antenna. Well, obviously you don't do as well as this. So this has been an issue for years. And the trouble is we only have one page to play with RadCom, so we can't do too much. So a few years ago, I got my head down and sat there with a pen and paper and thought, well, what we need to do is give people an opportunity to basically specify what station they've got. So, and then we would use an online program to do it. So the first thing we did was I chatted to OH6BG, I think it is, in Finland, who's the programmer for VOCAP, and told him what I wanted, and he came up with a system. So I'll come to that in a sec. I just want to show you a close-up of one of these RadCom tables. So you can see there, if you've got a dot, that means you probably can't work that part of the world. But if you've got a colon, you probably can work on FT8 or FT4. If not, it's going to be speech or sideband, and this is the likely, basically the signal strength you're going to get. So looking at Wellington, New Zealand, on 5 megahertz, is that? Or 7 megahertz, isn't it? Yes. Not likely to work at all. This is April's, I think. So, but on 10 megs, you do have a slight chance to work it at those sort of hours there, right about there. But anyway, so the point I'm making is these are very useful tools, but they're a bit, well, we're trying to be everything to everyone, and that's not really what's going to work. We needed to make it so that you could specify your station specifically. So went back to OH6BG and said, look, what can you do for us then? So he said, okay, so what about if we give you a chart like this? So basically you put the frequency that you can operate, the month you want to operate. You can put your noise level in, you can put your antenna gain and your power and your mode, and then I'll make it generate colored charts for you. So these are specific to you. So that's what we decided to do, and you end up with a chart like that. So what we suggest you do, if you're keen, is once a month you put all your details into one of these this chart and print out these color chart. You can keep it as a PDF file, and so you can look at it. So now these are basically designed for you and your state. So whether you are running a very poor station with low power, running a mega station with 4-element Yagis at 200 feet or whatever, no kilowatt, you can produce charts that are optimized for your particular location and power and mode. So that's what we decided to do. Now, we've done features on this in RadCom, and there's a page on RadCom that says online predictions where it will give you the links to this. But basically, it's rsgb.org/VOCAP. And then there's another tool as well called ionosphere Prop, which is a mouthful. So we renamed it Proppy. And so if you go rsgb.org/Proppy, it will do the same thing for you using this different tool, and you can print these color charts out for you. So there we go. So that's the point I wanted to make, really, is that we realize there's a limitation of what you can do with RadCom, because we've only got a page to play with. We haven't got much space. And we've looked at different ways of doing it and decided to leave it as it is and just concentrate on using the online tools. So you can either go to rsgb.org and it will give you a link to the RadCom tool for VOCAP, or the RadCom tool for ionosphere HF Prop called Proppy, and print off the charts that you actually need for your station. Or you can go to vocap.com or Proppy, which is at soundbites.asia. I think I'll show you the link for that in a second. Soundbites.asia, which will give you the ionosphere HF Prop program, and then you can specify where you are, what power you've got, and everything else, where you want to work, and it will give you a chart that you can use. So putting all together then, we're coming to the end now. So high solar flux index levels are generally good for HF, but solar flares, CMEs, which produce high KNA indices, are generally bad, which they result in high absorption and lower ionization of the F region. So what you find is that maximum usable frequencies come down as the K index goes up, and generally HF propagation is not so good. We had an instance of this a couple of weeks ago. It was the Commonwealth contest on Saturday, and that night before, we'd had a really bad auroral conditions. We'd had an A index up to 6 or 7, I think it was. And basically, that next morning, conditions were rotten. They were terrible. They were not good at all. Things did improve by the following day, but it was not a contest where people were going to get high scores at all. And people were generally disillusioned, I think, with how they were meant to do it. So the Chiltern ionograms, or solar flux, K-index, and solar wind speed, and BZ, which you can get all that information online. Solarham.com is a good one to look at. We'll give you a real-time indication of what the bands are going to be doing and what you should concentrate on. So you'll be really looking for a low solar wind speed, a BZ pointing north. That's the interplanetary magnetic field pointing north, not south. That will improve conditions for you. And finally, then I said spring, summer, autumn, winter are better than summer, as the ionosphere is cooler, denser, and the MUF is higher during the day. The ionic composition of the ionosphere is different in winter as well. Hello, I've just had a message come up from Malwarebytes. Let's put that out of the way. So, as I said, MUF is higher in the day during spring, summer, and winter. Summer not so good. Nighttime MUFs are higher in summer. So you may find that in summer, 20 meters stays open throughout the night. But in winter, it closes down shortly after sunset. And opposite is true in the southern hemisphere, which is why spring and autumn are good for trans-equatorial contacts. We're just past the equinox now. So this is a very good time of year for working north-south paths, such as UK to South Africa, or UK to South America. Probably the best time of all at the moment. But you may find that trying to work the US states, the United States or Canada, it's not so good nowadays. And we've got to wait until maybe October, November comes around to actually find those paths that open up. So if you want to work DX, it's best to know a little bit about propagation. You work at the best times to do it, which is why things like CQ Worldwide is held in October, because it's a best time for good propagation around the world. As the sun gets higher, D-layer absorption increases, but the MUF also rises. So follow the MUF up during the day and come down at night. So use the higher bands when you can during the day and the lower bands at night. Use the RadCom prediction tables, as I said, or go to VOCAP or Propy, which will both are free to use, and you can actually program in exactly what your station is. So you put in exactly what you've got in terms of antenna, power, noise levels, and that will give you a nice chart to show you the best times to work at. As I said, I've used it a lot, and I've recommended this that, for instance, trying to work at all states. It turned out that if you want to work Wyoming on 10 meters, there's about half an hour during the day when there was a good opening to maybe Wyoming. And if you didn't know when that half hour was, you'd be trying to guess what the best time to work propagation was, work Wyoming was. So it's very useful for that kind of thing. And thoroughly recommend that you use either VOCAP or Propy to do that. So I'll just leave this chart up for a little while if you want to make a note of those URLs. Also, I also keep monthly charts at G0KYA.blogspot.com. These are based on 100 watts to a dipole again, but when you go to, you'll see that you can just very easily click on a band, click on one of the times, beg your pardon, times, and you can just flick through it and see how propagation changes as you go on. So it's a very easy way of seeing how propagation changes during the day. And I update that every kind of 6 months with the latest smooth sunspot number figures. So there's actually 216 charts for each month on each band. So it shows you how much work is involved in producing them. I've got it pretty much automated now, but it's not the easiest thing to produce, but I keep it going anyway because it's a nice, easy look at chart, so you can actually see. Oh, I see that's why I can work South America this month on that band. Well, what happens if I go up a band, say from 17 meters to 15 meters? Oh, it gets better, or it gets worse. So it's a very, very useful little chart there. Very easy to use. You'll see when you go, you just click on the month, and then you click on the band, you click on the hour that you're working, and it will produce the charts for you. So that's a very, very quick introduction to HF propagation, and a very quick introduction to the tools that are available for you to actually use. But basically it comes down to two now, which is vocap.com and I2RHF prop, or as we call it, proppy, it's easier to say, at soundbites.asia. But at this point now, I'll open it up to questions. And we'll see if there's any questions out there. So if I click that one and stop sharing, there we go. All right, so any questions?
Yeah, Steve, that was absolutely excellent. Thank you. You just mentioned some URLs earlier on in the presentation. I think one was UK SSDC or something like that. Is that? I didn't quite catch the full URL on one of your slides.
UK SSDC. I'm not sure what that one. I talked about solarham.com. Definitely.
Right, okay. Oh, it might have been one of your sources or something like that.
Yeah. Yeah, I'm not too sure which one that was. The Chiltern ionosonde is actually. Let's have a look here. I've got it. Got it on a shortcut. Yeah, there are lots of sites that you can use that generally. swpc.noaa.gov is the Shortwave Propagation Prediction Center in America. Use that a lot for GB2RS to work things out. So again, that's swpc.noaa.gov. That's a good site. Lots and lots of stuff there. The Met Office has a space weather page as well. If you do Met Office space weather, that will take you there. The only problem with the Met Office, and we've discussed this at length, but they only do propagation predictions up forward for 4 days, 3 or 4 days, which is not really enough for what we need. Where else have we got? I'm just trying to find the Chiltern ionosonde. Oh, here we go.
Oh, he just booted himself. Anyone else still there?
Yeah, I'm still here. I forgot I was muted briefly there. I'm sure he'll join again in a second, or
I think I managed to scribble all those down anyway, so I can. Does it store this chat, Owen? Do you know?
no, I don't think it does.
No worries. I can. I'll save them anyway. I've got them all scribbled down.
Ah, brilliant. Well, maybe he just wanted to make a flashy exit.
The band closed.
He's rejoined, hasn't he? Yes, he has.
Ah,
Yeah.
brilliant.
Right. Can you hear me now?
We can see.
Welcome back.
Yeah. No, I am there. Close the tab, I think, accidentally. What was I saying? I was talking about the Chiltern ionosphere, wasn't I? That's the trouble with these. You don't realise that people can't hear you. So Chiltern Digisond. I'm gonna be careful now. I don't want to do it again. Bookmarks. Show bookmarks bar. Here we go. Right. Yeah, UK SSD was the URL for that. Show all bookmarks. There we go. Nothing to show here. Oh, great. That's good. Oh, dear. Can you still hear me?
Yeah, can still hear you, Steve. Yeah.
Oh, good. Yeah, sorry about that. Yeah. Okay, if you search for Chiltern Digisond, that will give you the link to that. I was saying the only problem with the Chiltern Digisond is it's not the best available at the moment, to be honest. So we generally use the DORB, D-O-U-R-B-E-S, DORB Digisond, which is in just the northern part of Europe for information. But yeah, there's Digisonds all around the world, so you can pick and choose and pick one that you want or not. All right, let's have a look what we got. All my bookmarks have disappeared. I don't get it. Why is that? I don't know. Right. Okay. I'll tell you what I'll do is I'll dig up the URLs and I'll send it to Rowan and he can pass them on to you. How about that? Probably the best
that'd
way
be
to do
perfect.
it.
Thank you, Steve. I
Yeah.
think I managed to scribble most of them down, but yeah, I just missed a couple right at the start.
Yeah, it's odd. I don't know why, but all my bookmarks have vanished. Show all bookmarks. Yeah, they're all gone. Isn't that weird? Strange. Yeah. Okay. Well, I'll give you a list of bookmarks and send it through to you. So, any more questions? No. Okay.
Nobody?
That's fine.
What? I got a question. What do you think about the DXView map?
DXView. Let's have a look, should we? DXView. I mean, these things. There are quite a few tools around, but DXView. Oh, here we go. DXLab. I mean, these are all quite good. Oh, I see. There we go. Yeah. It's okay. Generally, I prefer VoACAP and Propy for doing that sort of work. I mean, the thing is, you can either come up with a prediction program, a propagation prediction program, or you can use a live site that's using real-time contacts. So it depends on what you're trying to achieve, I think, really. The only trouble with the live ones is that generally they either work from RBN spots or they work from DX Summit, sort of, what am I trying to say? DX spots, what do you call them? Clusters, that's it, clusters. So I think they are better because they're showing you real propagation in real time. But as I said, if you just want to make sure that it's actually doing what you want it to do, because you might be looking at RBN, which is not much use if you're trying to work sideband, or you might be looking at whisper signals. So again, there's a big difference between hearing a 5-watt whisper signal and trying to hear a 5-watt SSB signal. So it's all a case of, knowing that what you're trying to do and, are we achieving it? So yeah, I mean, that's not bad, DXView, but there are so many of these things now.
Yeah, I did have a play with VoACAP still. I've not.
Yeah,
Not something that I'd heard of before tonight. So.
Yeah, well, VoACAP and ionosphere Prop or Proppy are gold standard really for propagation prediction programs, and they are pretty accurate. But what you just generally find is that obviously that they are based on the smooth sunspot number for that particular month. But if you've got a high K index, you probably find propagation is going to be an awful lot worse than they say, because they generally don't calculate things with K indices as well. So that it's like everything; it's a tool, but it's not the end of the world. You know, it's not perfect. But then again, using things like RBN is well. The thing is, sometimes you can't see a path by using RBN, but that's because nobody is using CW at the place you want to run to, for instance. So yeah. that's another one that doesn't necessarily work for you. You know, obviously you've got to have somebody making the contact to come up on DXView and whatever. So it's tricky. You know, it's difficult. So that's why I tend to go for propagation prediction programs that will show you the likelihood of a path between you and wherever you put your spot. But there we go. DXView is not one I'm actually not that familiar with. Is that a program you run? Rate this program at DX. Oh yes, I see it runs on PC. Yeah, okay, good. Yeah. No, it's not bad. I mean, it's kind of a sort of step up from VOA Prop, but yeah.
I see. It uses a combination of WhisperNet, reverse beacon network for MD8, PSK reporter.
Yeah.
So it's a bit of everything. I think they feed into it.
Yeah, yeah. But that's the problem, I think. So if you've got Whisper going into it, that's probably going to overstate the possibility of a propagation path between your 2 points, because Whisper can hear stuff below the noise, and they're all going to be low power transmitters. So that's a problem really that doesn't really come up in real life. In other words, it's not real life, is it? But yeah, it's horses for courses, Yeah. Any more questions?
Steve, you sometimes get like crazy good propagation after a CME. Is there any predictability with that, or is it just you just got to ride the wave as you get it if it's good, sort of thing?
That kind of pre-roll enhancement, as we call it, is well, you can kind of predict it, because if you know that something is coming, CME is coming, then you can sit and carefully watch the K index. Or sorry, let's start again. You can watch the solar wind speed. As the wind speed picks up, then you can look for an enhancement, because then probably about an hour after that, probably conditions will get a lot worse. So if you really, really want to play with this, then keeping an eye on solarham.com or ACE-HF solar wind speed, and just watch for it to pick up. So usually we can predict CMEs and other sort of solar effects a few days in advance. The only problem is, and this comes in another talk I give, which is that yes, we know that a solar flare has occurred, and we think there's probably going to be a CME, but until that actually hits the first spacecraft, we don't know what the speed is. And that could be anything from 400 maybe kilometers per second to 800 kilometers per second. So on average, it works out about maybe 1 to 2 days after a CME erupts from the sun. So that's the kind of the time you need to look at. Does SOHO not measure the speed? Yes, I think it does. But as I said, you don't know what the speed of the CME is until it hits the SOHO satellite. So again, it's a little bit iffy. Once it's hit the satellite, then you probably know it's going to hit the Earth shortly after. So depending on what orbits it's in. So by then, it's pretty much hit us maybe shortly after hitting the satellite. It's just so fast, and that's the trouble, when you've got the CME coming in at 1.5 million miles per hour, That doesn't take long. And you do get some CMEs that are very, very fast indeed. And they can traverse the Earth to UK, Earth to Sun distance in a day, maybe, where others might take 2 days. But yeah, it's interesting. But there is definitely, you can get a pre-auroral enhancement. So look for that CME to hit probably before the K-index even goes up, because obviously, say you got a measurement of the CME, the K-index at midday, you won't get another one until 3 o'clock, 3 p.m. So what happens between midday and 3 p.m.? Well, you don't really know, unless you keep an eye on the solar wind speed and look for that to go up. It's an interesting thing. It's probably, there's room there for an awful lot of research for propagation purposes as well. But yeah, sometimes you can be on the bands and you'll hear this thing. You'll hear conditions are getting much better, and you think, well, this is good. We're up for a good afternoon here, and then it will just die. The MUF will drop, and that's probably why. And then you'll see the K-index go up, because it obviously 3 hours after the CME hits or thereabouts, the K-index is affected.
Yeah.
So yeah, I haven't. What's today? Tuesday, isn't it? I haven't actually sort of looked at what's going on in the world for GB2RS. I generally do GB2RS on Thursday mornings, so that's when I get a better idea of what's going on. Let's have a look. I'm just looking at solarham.com now. So the K-index is now about 2-ish. Solar flux index 124, so not particularly good. Let's have a look at the real-time solar wind. Let me share this. I'll have a look. Share your screen. Right, here we go. Right, okay, so I'm now sharing real-time solar wind. So this is from the ACE spacecraft, I think. It might be SOHO, don't know. But you can see that there's the BZ, so you can see it's very, very south there. Then it goes up to neutral, and it's kind of neutral from there on. That's why the K-index is now low. Density is low. Speed has been fell up to sort of 650, is now tailing off. So again, this says to me temperature is tailing off a little bit as well. So it's tending to say conditions are going to be more settled. So the K-index over the next day maybe is going to be a lot lower than it has been in the past few days. Let's have a look at this one. Now you can see what sort of things you get. So the BZ here, you can see it going up and down like a yo-yo. So with the BZ south like this, and where are we? It's the speed. Oh, there's the speed. Very, very high indeed. So this was 23rd of March. That can't be right. No. 23rd of the 3rd, 2026. Oh,
last night.
Yeah. So I was just thinking. Yeah. So conditions there showing that the speed was very, very high indeed. Oh, hang on. Let's think about this. So yeah, so the K-index was high last night, and you can see why now. So yeah, I suppose if you're trying to find these pre-auroral enhancements, this is the best way to do it, is look for when the solar wind speed goes up and the BZ points south, and that is probably when you'll get the pre-auroral enhancement. You may not get it all the time, but yeah, if you do see it, then work it, because it won't last long, because MUFs will go down. But I didn't mention it, but PropQuest is another site, propquest.co.uk. This is produced by Jim, G3YLA. Share this tab instead. Here we go. Right. So there we go. This is a chart of the MUF today using the Dor Digisonde, and you can see that the MUF has been quite low today because of the effects last night. So it's never really got above about 24 megs. So today, 10 meters has not been a good band. looking at this. You might have found the odd DX station, but there wouldn't be much activity on 10 meters, I don't think. But if we kind of go into the archive and scroll back a few days, we'll find it probably gets better. 21, let's try that. Oh, there we go. So yeah, you can see there the MUF has over 3,000 kilometers has gone up and down. So it's got as low as 18 megs there, and as high as 28, is it? There we are, 28.6, just at that point there. So sort of 5 or 6 o'clock. So this is another good PropQuest. Again, it's free to use, is a very, very good indicator of the maximum usable frequency that you are likely to be able to hear. And you can see that this was a couple of days ago, 21st, and yeah, MUF got up to 10 megahertz, but today, let's press that again, you can see that never really got much above 21 megahertz. And then you can see some odd goings on. Get the thing out of the way. You can see that there's some disruption going on there. It's 0300, 0400, and that's probably when the CME hit. And then you can see that the MUFs, even after sunrise would have been about there. MUF there would have been about 12 megahertz. So conditions were not probably very good on HF today. I haven't actually listened today. So, and then you can see now it's tailed off. So just 14 megs is probably still open over a 3,000 kilometer path. But it will close fairly soon. It will go down to 7 megs again there. But yeah, we got a real problem because RF Fairford used to have a digisond, but the Americans decided not to publish the information or release it, so we can't use Fairford anymore. And Chiltern, if I switch off Daub, you'll see what I mean. If I switch on Chiltern and refresh it, there we go, there's nothing. Because Chiltern, which is the Rutherford Labs Laboratory digisond, is not actually online supplying the database that we use. That's only the Daub one. So we have to use Daub, which is Daub, I think is Belgium, I think, to give us all our data. So that's how we managed to produce these charts. So this, again, this is quite useful. You can see exactly what's going on. And if we click on this NVIS, near vertical instant skywave shot, it will show you the FOF2 or the critical frequency. So that's the red plot. So you can see there that the red plot has been 6.625 megahertz, 6.5 megahertz. So again, it shows you that 40 meters was probably okay over about 500 kilometers path, or maybe from the south to the north of England. But if you're trying to work a guy who's 50 miles down the road on 40 meters, it probably wouldn't have worked for you. But again, that's probably down to just the time of, or this particular day. If we go back to the 21st, I think, I'm guessing now it'd be higher. Oh, here we go. Yeah, 7 megs. So look, you can see here that the critical frequency there has got up to 7.5 megahertz, 8 megahertz there. So you probably find that 40 meters is working very, very well for you, at least from 9 o'clock till 6 o'clock. But today's not been a good day because we had this disturbance last night. But there we go. So that's propquest.co.uk. Again, it's a free service for you to use, and that's Jim G3YLA has done it. We discussed what we want, and he had a programmer working for him who did all this. He's now moved, unfortunately, so we're not likely to get it updated very often. But Jim also does a sporadic E blog from May to September. So if I click on the E's blog there, it's oh, there we are. He's updated it now. So welcome to the E's blog page of PropQuest. The usual format is I write a daily blog from 8 August dealing some of the features. And he also shows you these maps. And this is will give a prediction of where he thinks sporadic E will occur, or what paths. But he tells you more about it in his blurb, so it's best to read that. But that doesn't come into effect till about the 1st of May, really. But there we are. So, yeah, I generally don't talk about PropQuest during this particular talk, because otherwise it just goes on and on and on. But you get the idea. It's another good tool to use anyway. Can't remember what the question was now, but I think we covered it.
Yeah, you did. Yeah, cheers, Steve.
Good, thank you.
Yeah, Steve, I have a question for you. Graham here. I read the GB2RS news and do your do your report every week. I have a question about optimizing coverage for the UK, because I do the national news,
right,
which goes out on 5 megs, and I also do the 3.5 megs news at 8 in the morning, right, which is for Midlands and East Anglia. And I was just wondering, for the NVIS type propagation, is there anything I can do to improve coverage between, say, summer and winter time regarding antenna height, sort of launch angle? Is there any study on that?
Right, okay. Well, thinking about this out loud, with NVIS you need a high angle of radiation. That's what NVIS is all about. But you also need to know what bands are open. Like I just showed you 2 days ago, 40 meters would probably have been working around the UK quite well. Today it wouldn't have been. And it's very hard to predict, because it's down to CMEs basically. So yeah, it's 5 megs was always a good band for NVIS. Generally, as long as we don't have any CMEs. So 3.5 megs is a good band in the winter, autumn and winter, definitely. But probably not a good band for doing it in the summer, spring and summer. But 5 megs probably right now, I'm guessing, is probably the best band for reliable around the UK propagation. If not 7 megahertz. But as I said, as I showed you, that 7 megs probably wouldn't have worked today. So it's very tricky. You need to know exactly what conditions are like for that particular time, and it will change month to month, and it will change from day to day. So I can't say to you, yeah, definitely use this band, it will work the treat, because it will vary.
Yeah, no, well, the band itself, I can't vary that, because the you know, it's a news schedule it's on 5 megs and it's on 80. I was just wondering about the antenna height in order to optimize the coverage and to get the optimum launch angle. Is there anything I could consider? Because I've got the antenna on a halyard, and I can raise it up and lower it down. And
well, what you can always do is just do some tests yourself, or between 2 of you, to try it at different heights and see what sort of signal strengths come back down. I mean, it's a tricky one, because the lower the height of the antenna, the more high angle it should be. But there is a point where it starts to fall apart. The trouble with 5 megs, 60 meters, is maybe a dipole below a half a wavelength high would be good for NVIS, but half a meter high at 60 meters that's 30 meters. That's quite a long way up, actually, 100 feet.
Yeah.
So so you could start at 100 feet and start to drop it, but then it gets a point where you're getting ground absorption. So there will come a point where obviously it's on the ground and you're not getting anywhere at all. So there must be an optimum height for that to work. Yeah, tricky. It's I think the only thing or the best thing to do is play with it and see what works for you. That's not a terribly scientific answer, but I don't think there is a book that says, oh yes, it needs to be at this height to get this distance. And what you may find is you drop it too far, then stations which are further away from you may not be able to hear you. So it needs to go up a bit just to bring that angle down a little bit to get the distance you want. But yeah, that's a good point. It's something worth playing with playing with at different heights to see what effect it has on the signals.
Okay. Yeah, it's difficult because conditions are so changeable. When you do a test one week, next week the test might be completely invalid. And I was just wondering if there's like a smoothed average value that would be about right for winter and about right for summer.
Yeah.
To get as much coverage of the UK as possible.
The guy in Propagation Studies Committee who does most of this work on 5 megs, he actually did a lot of the research work on 5 megs, so is Marcus. I'll drop him a line and see what he suggests. That's interesting. It's an interesting proposition.
Yeah.
How high should your antenna be to get the optimum propagation around the UK on 5 megs?
Mm.
I'll ask him the question, see what he says.
Okey-doke. Lovely. All right. Well, thanks ever so much, Steve.